Hey guys! Welcome back to the laboratory. In this video, we are looking at cracking. By the end of this video, you should be able to define the term cracking, describe what happens during cracking, and explain why cracking is necessary. So, let's go. Cracking is a chemical process used to break down long-chained alkanes into shorter, more useful hydrocarbons. Shorter hydrocarbons make much better fuels because they have lower boiling points and so are much easier to ignite, in comparison to longer hydrocarbons that are much harder to ignite and therefore not as useful as fuels. The fractional distillation of crude oil often produces more longer hydrocarbons than is needed. In simpler terms, the supply of the fractions after the fractional distillation of crude oil does not meet the demands in the industry. Cracking hydrocarbons is necessary because it allows the demand for particular fractions to be met. Cracking is often carried out via one of two methods. These are thermal cracking or catalytic cracking. Thermal cracking uses a combination of high temperatures and high pressures. The temperature ranges from around 450 degrees Celsius to 900 degrees Celsius, and the pressure used is around 70 atmospheres. Catalytic cracking heats the alkane to around 650 degrees Celsius, causing the alkane to vaporize. The vapors are then passed over a catalyst containing aluminium oxide, which causes the bonds in the alkane to break and reform. The cracking process is entirely random and will always produce at least one alkane and one alkene. Both alkanes and alkenes form homologous series of hydrocarbons. However, an alkane is described as being a saturated hydrocarbon because there are only single bonds between its carbon atoms, whereas an alkene is described as being an unsaturated hydrocarbon because there are double bonds between its carbon atoms. Alkenes are very useful in the industry for making different polymers such as plastic. So, if Decane were to undergo a cracking reaction, the products of the process may be butane with chemical formula C4H10 and hexene with chemical formula C6H12. We could represent this reaction using a word equation. The word equation for this reaction would look like this. Note that the law of conservation of mass applies to these reactions too. At the start of the reaction, we had 10 carbon atoms and 22 hydrogen atoms. At the end of the reaction, we still have 10 carbon atoms and 22 hydrogen atoms. No matter has been lost or gained. Now remember, the cracking process is entirely random and may produce any combination of short-chained hydrocarbons. In our previous example, we saw decane break down into butane and hexene. However, another possible outcome of this reaction may have been the production of pentane, propene, and ethene. The word equation for this reaction would look like this. Again, take note of the fact that the number of carbon and hydrogen atoms at the start of the reaction are the same at the end of the reaction. This is because the mass has been conserved. Here's an example of a past paper question that I'd like for you to attempt to test your understanding of the content covered in this video. Pause the video and take your time to work it through. Press play once you're ready to check your answers. Let's start by answering our first question. Alkenes can be obtained by cracking some fractions obtained from crude oil. Explain what is meant by cracking. A nice, easy question to get us started. You should have noticed that there are 2 marks awarded for this question, so that means the examiner is looking for 2 key points to award the full marks here. So, our first mark is for stating that cracking involves longer molecules or longer hydrocarbons being split, and our second mark is for stating that they are being split into smaller molecules, or alkanes, or alkenes, or hydrocarbons. The second part of this question states, Decane with formula C12H26 can be cracked to form useful products. Calculate the equation for the cracking of Decane by filling in the formula of the single molecule needed to balance the equation. Again, another nice question, this time for 1 mark. Now, we know that the mass must be conserved in this reaction. What we put in is what we get out. And so, we need to make sure that the number of carbon and hydrogen atoms at the start of the reaction are exactly the same at the end. This number here is very important, and I hope you didn't overlook it. This number is telling us that we have 3 molecules of C2H4 in our products. If one of those molecules has 2 carbon atoms and 4 hydrogen atoms, that means that 3 of these molecules would have a total of 6 carbon atoms and 12 hydrogen atoms. We started the reaction with 12 carbon atoms and 26 hydrogen atoms. The remaining atoms must be in the compound that we are being asked to complete the formula for. 12 carbon atoms minus the 6 carbon atoms from our 3 molecules of C2H4 gives a total of 6. Our compound has 6 carbon atoms. And 26 carbon atoms minus the 12 from our 3 molecules of C2H4 gives a total of 14. Our compound has 14 hydrogen atoms. Our answer to this question is C6H14. So, how did you do on this question? Let me know in the comment section below. Anyway, that's it for this video, guys. Thank you for joining me in the laboratory. Please leave a like on this video if you found it useful, and don't forget to subscribe to the channel so that you don't miss another one. See you soon.